Welcome to TRIUMF. TRIUMF is Canada's National Laboratory for Particle and Nuclear Physics. It's located on the campus of the University of British Columbia. My name is Susie Lappy, and I'm a researcher in radiopharmaceuticals.
My name is Marcello Pavan, and I'm a scientist in nuclear astrophysics at TRIUMF. In today's program, we will demonstrate Einstein's theory of special relativity. Some of the ideas of relativity may seem strange and impossible, but here at TRIUMF, we know that special relativity works because we see it in action every day. In today's experiment, we hope to let you experience how particles behave when they travel near the speed of light.
At TRIUMF, we study the atomic nucleus and investigate how matter is put together. We study the decay of short-lived subatomic particles. We recreate the nuclear reactions that form new elements in exploding stars. And we make radioactive isotopes for medicine that allow doctors to see what's happening inside the human brain. And we use high-energy particles to treat cancer. To do all this, we need high-energy particles, high enough in energy to smash atomic nuclei apart. These particles are produced by a giant circular particle accelerator called a cyclotron. The TRIUMF cyclotron uses powerful electric and magnetic fields to accelerate protons up to 3/4 of the speed of light. That's already pretty fast, but to illustrate relativity in action, we will make particles that are going even faster, over 90% the speed of light. We do this by making the high-energy protons from the cyclotron collide with a carbon target to make even faster particles. We can measure how long it takes for particles to travel from detector A to detector B. By directly measuring the velocity of particles with a certain momentum, we can compare what we measure with relativity's predictions. At speeds that are slow compared to the speed of light, the momentum of a particle is given by the formula P equals m times v. This formula for momentum is accurate for everyday objects like cars, airplanes, and even rockets, but we will show in today's experiment that when particles are moving near the speed of light, this formula is no longer accurate.
To make these fast particles, we take the high-energy protons from the cyclotron and slam them into a carbon target. The carbon target is made of carbon atoms, each of which consists of electrons orbiting around an atomic nucleus. The nucleus is made not only of protons and neutrons, but also other subatomic particles that you may not have heard yet. These particles are called mesons, and they act like a nuclear glue to hold the protons and neutrons together inside the nucleus. There are many kinds of mesons, but the particular kind that we will be using are called pi mesons, or pions for short. When the high-energy proton hits the carbon nucleus, it blows the nucleus apart, and the pions come flying out. These pions have a mix of different velocities. The pions also come in positive, negative, and neutral charges. Pions are very short-lived particles, and many of them will decay in a few billionths of a second, producing other particles called muons and electrons. The muons and electrons also come in positive and negative types. So what we have coming out of the target are pions, muons and electrons of both positive and negative types. Now the particles emitted in a certain direction are collected in a beam pipe and enter the bending magnet in the beamline. The bending magnet causes negative particles to bend to the left and the positive particles to bend to the right. Our beamline bends to the right, so we have only positive particles coming down the beamline and into the experimental area. The negative particles just smash into the wall of the magnet and get absorbed.
Not only does the bending magnet sort the negative particles from the positive particles, it also picks out particles of one momentum. We'll give a simple graphical explanation of how this works, and if you want a more detailed mathematical explanation, you can find it in the supplementary material. Basically, the magnetic field exerts a bending force on all of the moving charged particles. This bending force makes the particles travel in a circular arc. The higher the momentum of the particle, the less rapidly its trajectory bends, and the larger the radius of the circular arc. Consequently, a high momentum particle bends too little and misses the beamline. A low momentum particle bends too much and misses the beamline. But a particle of just the right momentum bends just the right amount and goes straight down the beamline. So all of the particles that we have coming down the beamline all have the same charge and the same momentum. If we wanted higher momentum particles to come down the beamline, we increase the strength of the bending magnet. This makes all the particles bend more than they did before, and now the high momentum particle that didn't make it before can go all the way down the beamline. By increasing or decreasing the strength of the bending magnet, we can make higher or lower momentum particles come down the beamline.
Now that we have a way to get particles of the same electric charge and the same momentum to come down the beamline, we need a way to detect the particles. The particle detector that we will use is called a plastic scintillator. It is just a slab of clear plastic which contains fluorescent materials. When a particle passes through the plastic, it excites the molecules of the fluorescent material, and a few nanoseconds later, they de-excite by giving off light. I can show you what that looks like by using an ultraviolet lamp to excite the plastic scintillator. The actual light flash caused by a particle passing through the plastic scintillator is extremely faint, so the scintillator needs to be wrapped up in aluminum foil and then black plastic to keep the room light out of the detector. The big black cylinder attached to the scintillator is a photomultiplier tube, which converts the faint flash of light into an electrical impulse. The more light, the bigger the electrical impulse. We want to measure the velocity of the particles, so we place two of these plastic scintillators 4.4 meters apart. When a particle hits the front scintillator, it makes a flash of light, which gets converted into an electrical impulse. This impulse goes to the start button of an electronic stopwatch. Some nanoseconds later, the particle hits the back scintillator, which makes an electrical impulse, which travels to the stop button of the electronic stopwatch. So now the stopwatch measures how much time it takes for the particle to fly from the front scintillator to the back scintillator. Since we know the distance to be 4.4 meters, we can use the formula velocity equals distance divided by time to calculate the velocity of the particles. Since the particles travel so fast, the time t will be very short. So we will measure time in units of nanoseconds, where 1 nanosecond equals 1 billionth of a second.
So far, we have been looking at animated cartoons of this process. Here's what the actual apparatus looks like. First, here's the cyclotron, which produces the high-energy protons. Since the cyclotron produces a lot of radiation when it's operating, it has to be surrounded by concrete shielding blocks to absorb the radiation. Here's a view from outside the shielding blocks. Over to the right is the cyclotron, under those yellow shielding blocks. Running along the far wall of this building, there is the beam tube which carries the high-energy proton beam. It is also covered up by yellow shielding blocks. Buried under the blocks is a set of bending magnets, which, you remember, selects charged particles of one particular momentum. Now we see the beam area, where our plastic scintillator detectors are located. We now go down to the beam area to have a closer look. Here's the front plastic scintillator, and here's the back plastic scintillator. If there were particles flying down the beamline while we were standing in the beam area, we would be exposed to a dangerous level of nuclear radiation. Therefore, beam delivery is prohibited when people are in the beam area. To enable beam delivery, we have to evacuate and then lock up the beam area. The siren blares to warn anyone still in the beam area to get out, and simultaneously a red beacon flashes out a visual warning. Now we're ready to fire particles through our plastic scintillators.
Let's return to our electronic stopwatch. We will measure the passage time for many particles and make a bar graph of the times. We can build our bar graph one particle at a time by laying down building blocks. The horizontal axis measures the time t, and the vertical axis counts the number of particles at that particular time t. Suppose that for the first particle, the stopwatch measures 23.1 nanoseconds. We lay down a building block at t equals 23.1 on the horizontal axis. Suppose the next particle is faster and takes 19.8 nanoseconds. This time, we lay down a building block at t equals 19.8 on the graph. The next particle is faster still and takes only 14.7 nanoseconds. So we lay down another building block at t equals 14.7. The next particle is a slow one, which takes 23.1 nanoseconds, just like the first one. So we add another building block on top of the first one at t equals 23.1. We just keep repeating this for thousands of particles, and we end up with a graph like this. When we look at the bar graph, we see that there are peaks at t equals 14.7, 19.8, and 23.1 nanoseconds. This means that a lot of particles took about 14.7 nanoseconds to go from the front scintillator to the back scintillator. And a lot of them took about 19.8 nanoseconds, and a lot of them took about 23.1 nanoseconds.
So why are there 3 separate peaks in the bar graph? That's because there are 3 different types of particles in the beam, namely positive pions, positive muons, and positive electrons, which are also called positrons. All of the particles coming down the beamline have nearly the same momentum p, but they all have different masses. In fact, physicists have measured the masses of these particles, and here they are. In particle physics, we don't measure particle masses in kilograms because then we would end up with absurdly small numbers. We measure masses in units of MeV per c squared, where 1 MeV per c squared equals 1.783 times 10 to the minus 30 kilograms. You can just regard these as weird units that physicists use. The supplementary material will give more details about these units if you are interested. So the electron is the lightest particle that comes down the beamline. It weighs about half of an MeV per c squared. The muon is about 200 times more massive than the electron, and the pion is about 300 times more massive than the electron. The proton and the neutron both weigh about 940 MeV per c squared, and they are about 2,000 times more massive than the electron. We also measure momentum in another weird unit, namely MeV per c. The conversion to SI units is 1 MeV per c equals 5.344 times 10 to the minus 22 kilogram meters per second. And we have already said that we measure time in units of nanoseconds, where 1 nanosecond equals 10 to the minus 9 seconds. So here again are the weird units that physicists use and the conversion to SI units. We measure mass m in units of MeV per c squared, and momentum p in units of MeV per c, and t in units of nanoseconds.
Now remember that all the particles coming from the beamline have almost the same momentum. If we use the non-relativistic formula p equals m times v, we see that the velocity equals the momentum divided by the mass. Since p is the same for all the particles coming from the beamline, regardless of whether they are pions, muons, or electrons, it's easy to see that the heavier the particle, the smaller the velocity. If we have a pion, which is the heaviest of the 3 types of particles, it's going slowly, so the stopwatch registers a long time between the start and stop pulses. If the particle were a muon, then its mass is smaller, so for the same momentum it would be going faster and the stopwatch would register a shorter time. If the particle were an electron, because it is so light, it would have to be going very fast to have the same momentum. So the stopwatch would register a very short time. So the 3 peaks in the bar graph correspond to the 3 different types of particles in the beam. You notice that the peaks are not perfectly sharp, but they have some width to them. That's because the momentum selection in the beamline is not perfectly sharp, and the apparatus for measuring the time of flight is not perfect either. Now let's look at some real data corresponding to a momentum of 120 MeV over c. Just like in the animation that we looked at earlier, the bar graph of the flight time shows 3 peaks. The peak on the left corresponds to a short time interval, therefore faster particles, therefore particles with smaller mass, which must be the electrons. Similarly, the middle peak corresponds to middle mass particles, which in our case must be the muons. And finally, the peak on the right corresponds to the longest time interval, therefore the slowest particles, therefore the heaviest particles, which are the pions. We make a note here of the positions of the 3 peaks. Electrons at t equals 14.7 nanoseconds, muons at t equals 19.8 nanoseconds, and pions at t equals 23.1 nanoseconds.
What happens if we select particles of a higher momentum? We can do this by increasing the magnetic field in the bending magnet. Let's look again at our data for 120 MeV per c. What do we expect to happen to the peaks when we increase the momentum? If the formula p equals m times v is true, then as we increase the momentum p from 120 to 140 MeV per c, we would expect the velocity v of each type of particle to increase as well, and therefore the time t of each type of particle to decrease. Let's look at the position of the three peaks at 140 MeV per c. Now at 140 MeV per c, the pions are t equals 21.1 nanoseconds, which is certainly smaller than it was for 120 MeV per c. The pion flight time has decreased by 2 nanoseconds. In other words, the pion velocity has increased. The muons are now at t equals 18.5 nanoseconds, which is a 1.3 nanosecond decrease in flight time. So the muon velocity has increased as well. But the electrons are still at t equals 14.7 nanoseconds, the same as for 120 MeV per c. So even though we increased the momentum of the particles, the electron velocity did not increase measurably. This demonstrates that the formula P equals m times v from classical mechanics cannot be correct.
Now, what is the explanation for this? The theory of special relativity says that the momentum equals the mass times the velocity, and that is only an approximation that is accurate for particles moving much more slowly than the speed of light. The true equation, according to special relativity, is P equals gamma times m times v. For slow particles, gamma is very close to 1, so we can't really tell the difference between classical physics and relativity for slow particles. But the particles that we are producing are going at a good fraction of the speed of light, so we might expect that we would be seeing deviations from the predictions of classical physics, and we have seen it already for the electrons. Classically, P equals m times v. Here m is the mass of the particle, which in our case is a constant. If we make a graph of P versus V, as we change to different values of P, we should get a straight line with a slope equal to the mass m. If special relativity were true, then P equals gamma times m times v, where gamma equals 1 divided by the square root of 1 minus v squared over c squared. And since gamma is a number that starts at 1 and gets larger and larger as v approaches c, the plot of P versus V should exhibit an increasing slope as V increases and gets closer and closer to C. Sometimes people call gamma times n the relativistic mass, because if you use the classical expression m equals P divided by V, it's behaving as if the mass were increasing as you approach the speed of light. Now let us show the bar graph of flight times for particles with a range of momentum, starting from the lowest and going all the way up to 220 MeV over c. In your handout material, you will have a set of the bar graphs. For your exercise, look only at the muon peak. That's the second peak from the left. For each momentum, determine t for the muon peak. Using the known distance d equals 4.4 meters and velocity equals distance divided by time, calculate the velocity v of the muons for each momentum. Then plot a graph of P on the vertical axis versus V on the horizontal axis, and see whether the graph looks like a straight line as predicted by classical physics or a curve with increasing slope as predicted by special relativity.